Hey everyone, hope everybody's doing well. Welcome back to the channel. This is Rob. Today's video is going to be on spanning tree protocol. So for anybody that's studying for their CCNA and they need to know the basics of spanning tree, if you're maybe a little bit confused about certain things, like I know I definitely was when I first started, hopefully after watching this video you'll have a much greater understanding and it will all make sense. What I'm going to cover is some of the bad things that can happen without spanning tree protocol, and how the election process works and plays out as far as electing a root bridge, figuring out what ports are going to be designated ports, root ports, and blocking ports. So let's start by looking at the topology that I have on my screen. And you'll see that there are 5 switches, and they are looped together. So we have a loop right here, and we have another loop right here. We also have 2 PCs connected to these switches right here and right here. And I wanted to start off by, well, first of all, I guess I'll start off by answering a question that maybe some of you might have, and that is, what is spanning tree protocol anyways? So what spanning tree protocol is spanning tree protocol is essentially a protocol that prevents layer 2 topological loops. So it will logically block a link if it detects a loop, so say like right here, just for example. And that way you don't end up with any of the problems that I'm going to show you here in just 1 second. It's also really good for redundancy. So that way if another link fails, spanning tree will just unblock a link, and you have that redundancy and that automatic failover in the event of another failed link or a failed switch. So let me go over some of the bad things that can happen if it wasn't for spanning tree. So let's just pretend for a moment that all of these switches in here are non-managed switches, just dumb switches, not running spanning tree, and we proceeded to have a loop in the network anyways. So the first thing would be duplicate frames. So let's just back up for 1 second here and think about what switches actually do. So what does an Ethernet switch actually do other than just providing a central connection point for everything in the network? So what Ethernet switches do is they forward frames, and they also learn MAC addresses. That's how an Ethernet switch is able to determine what egress port to send a frame out of to get to a certain destination. So let's pretend for 1 second that none of these switches have learned any MAC addresses yet. And again, no spanning tree is running. And I'm also going to cover this up for now because this doesn't have anything to do with anything I'm going over just yet. So anyways, no spanning tree protocol. None of these switches have learned any MAC addresses. Well, what's going to happen if PC1 wants to communicate with PC2? So we're going to send a frame to this switch right here. So again, obviously PC1 would have to have the MAC address of PC2. The switches would not have the switches would have to not have the MAC address in their MAC address table for this to work. Because otherwise, PC1 would send out an ARP to get the MAC address, and that would eventually fill in the MAC address tables because PC2 would respond. But then, of course, that would move on to another problem that I'm going to cover in just a few here, and that would be broadcast storm. But anyways, so PC1 already has the MAC address of PC2. None of the switches remember the MAC address. They don't have them in their MAC, or they don't have it in their MAC address table. So what's going to happen is if there's unknown unicast traffic that reaches a switch and the switch doesn't know the destination, it floods it out of every single port. If you want to get technical, floods it out of every port except the one that it was received on. So it would flood that frame out of this port, in this port, and that frame would be sent here, and then from this switch it would be sent here, and then we would get 1, 2 to PC2. So duplicate frames. Definitely undesirable behavior. Second thing would be flapping MAC address tables. So we'll take this switch right here and say the MAC address for PC1. So this switch, so a frame might come in through here, and this switch goes, okay, let me update my MAC address table. The MAC address for PC1 is located off of gigabit 0/2. Say another frame comes in this way, and the switch says, okay, I thought you were on gigabit 0/2, but okay, I guess you're on gigabit 0/0. So let me update my MAC address table. And the same thing happens back and forth, back and forth. Oh, let me update it back over to gig 0/2. And that will just continue to happen. So another undesirable effect in having a loop topology and not running spanning tree. Now, last but not least is the probably the most devastating consequence, and that is a broadcast storm. So what do you think would happen if, say, PC1 sent a broadcast out of its Ethernet 0 interface over to this switch right here? Well, this switch is going to broadcast that frame out all of its switch ports. And since this switch receives this frame on both gig 0/0 and gig 0/2, well, it's going to, the one that came in through gig 0/2 will then be broadcasted out of gig 0/0. The one that came in through gig 0/0 is going to be broadcasted back out gig 0/2. Of course, they're going to go this way as well. So it's also going to affect the resources of everything connected to the network also, such as PCs. Essentially, that's just going to loop around the network indefinitely. It's a broadcast storm. It's not like a layer 3 routed network where there is a time to live. So packets would have a time to live and they will be killed off after a while. Layer 2 doesn't work like that. It's an indefinite loop and it won't stop until either the link is unplugged, so you no longer have a loop in your topology, or the network just dies, all resources are exhausted, any one of those scenarios. Either way, you're not going to be sending much traffic through a network that's all congested due to a broadcast storm. So definitely the most undesirable thing to happen. Oop, I'm going to get rid of all this. So we have duplicate frames, flapping MAC address tables, and broadcast storms. So spanning tree exists to prevent that. So it will logically block one or more links, depending on the topology, to prevent that from happening. Another reason for spanning tree would be redundancy. So if you had a network, say it was set up like this, and you had unmanaged switches, and you wanted redundancy, you really couldn't have it to the point where it was automatic, because you would have these loops. So what you would need to do is have this, one of these cables, we'll say this one, have this cable unplugged, have this cable unplugged, and if there's a failure anywhere, you would have to manually go in and then plug that link back in and do the failover yourself. So spanning tree will do that automatically. if it detects that there is no longer a loop in the network. So say we were blocking here, and say this is the root bridge, and say this link right here were to fail, this switch right here would stop receiving BPDUs from the root bridge. The timer would expire, and then we would move from a blocking to, well, if it's class expanding tree, we would move through the learning and listening states, and then we would eventually move over into non-blocking. So that would be automatic. Okay, so preventing loops so we don't have any of those bad things happen, and also for redundancy. So you're thinking, okay, that's great, but I came here, I already know all of that. I came here to figure out, well, how does spanning tree work? I need to get this down and remember it. You know, how is the root bridge selected, in the different ports decided? So I greatly simplified this example. So if you look at these, this would be the bridge ID. So the bridge ID is comprised of the priority and the MAC address. Default priority is 32.768. And I have greatly simplified the MAC address to make this much easier to understand and much easier to point out the priority of these switches. So with that being said, root bridge is elected by the lowest bridge ID. It's as simple as that. There's no gotchas or anything. It's lowest bridge ID. It's unless you have a switch in your topology that somebody has configured statically as the root bridge, which isn't the recommended way to do it. If you want to ensure a switch is going to be the root bridge, the best way is just lower this priority all the way and set it at like 4096, I believe is the lowest you can go. And that should guarantee you that switch will become the root bridge. Other than that, there's nothing hiding. There's no other, this, but then this could play a factor in it. No, it's the lowest bridge ID is how the root bridge is determined. So don't be thrown off. Don't feel intimidated by this. It's very simple, and that's also why, again, I simplified these MAC addresses, and the priorities are all the same. They're all the default of 32.768. So it should be pretty simple looking at this topology, figuring out which one has the lowest bridge ID. So I'll actually just pause here for a moment and let you look at this, or if you want to pause the video and see if you can figure it out on your own before I proceed. Okay, so if you chose this switch right here, then you were correct. So this switch right here is going to be root. And that is because it has the lowest bridge ID. So default priority, 32.768. All of these are 32.768. And then we have, in our simplified MAC address, 1, 2, 3, 4. Apparently I skipped over 5, so 4 and 6. So clearly this is the winner. Now, if we had another switch in here and say this was 4096, and I apologize, I'm trying to write with my mouse. The priority was 4096, then this would be the root bridge, because this priority right here would be lower than any of these, and that would be that would automatically be the lowest bridge ID. So root bridge, lowest bridge ID. Bridge ID is the priority combined with the MAC address. Now, once the root bridge is selected, these ports right here, they automatically become not root ports, The root ports would be on the switches on the upstream interfaces pointing towards the root bridge. And the root bridge itself, all of its interfaces will be designated ports. And let me see if I can just make this a little bit nicer. Okay, designated. So we're all set on this. Root bridge, all interfaces are designated ports. So let's look at these other switches. So we will move on to this one right here. So first of all, we want to determine, well, what port is going to be the root port. So which interface has the best path to the root bridge? The best cost? Just the best way to get there. Don't overthink it. It's literally the best, the quickest. And yes, bandwidth definitely plays a role in this. So if we had, actually, again, I said I'm going to keep this basic, so I'm going to keep it basic. But these are gigabit links. I believe the cost is for... What's happening? Okay. So the cost on all of these links will be 4. So if we look at this switch right here, it's a cost of 4 to get to the root bridge. Even though I'm not going to go around and put a 4 on every single one of these, it's the same. So we know that this would be 4, this would be 4, this would be 4. So if we go this way, it's a cost of 4. If we go this way, it's a cost of 4, 8, and 12. I'm sure the majority of people would agree with me that 4 is lower than 12. And with that being said, that would make gig 0/1 on this switch the root port. R right there. All right, now let's move over to this guy right here. So it's kind of the same thing as it was on this switch. Root port, we can either go this way or we can go this way. It's going to be the same. It's either a cost of 4 or it's a cost of 12. So clearly, gigabit 0/2 is going to be the root port. All right, so we have, on the root bridge, we have designated port. On these switches right here, we have our root port. So let's move down and take a look at this one right here. This is where we're going to implement what we call a tiebreaker. There are a couple different tiebreakers when deciding, well, pretty much deciding anything in spanning tree. So the most likely time you're going to encounter a tiebreaker is deciding a root port. And this is going to be the perfect example. Because if we look, we have the cost is going to be tied. So if we go this way, out gig 0/3 and then out gig 0/1, it's going to be a cost of 8. And if we go this way, again, it's going to be a cost of 8. Now, let's say one of these links was a 10 gig link or something like that, then it may be different. But being that the cost is the same because these are all 1 gigabit per second links, it's going to be a tie. So How do we know? How do we know which port is going to be the root port? Are they both going to be the root port? Well, no, they're not. You can only have one root port per switch. So the way that the tie is broken, so the first tiebreaker is going to be bridge ID. So this being a possible path to the root, this being a possible path to the root, out of these two, which one has the lowest bridge ID? And that is going to be the first tiebreaker. And we don't have to move beyond that tiebreaker right now, because if these were the same, which would be extremely unlikely, but you're actually going to see an example of that down here, which is why I did this, in case anybody was looking at that, like, why would you set that up like that? But yeah, for this one, we don't need to move beyond that because this switch has the lower bridge ID. And with that being said, that's going to make gig 0/3 a root port. So put an R right there, and automatically, if this is a root port, well, we know this port is not going to be, this port can't be blocking because it needs to pass traffic to be able to get to the root bridge. So automatically, that's going to make gig 0/3 on this switch over here a designated port. So I'm still ignoring what's down here. So don't pay attention to that yet. That's going to be the last step. So now we're at the point where, just looking at these four switches, we have decided a root port on every single one of them. So now, if you want it to be basic, you could technically say that, okay, well, that means that this link right here is gone, blocked. And that wouldn't necessarily be wrong to say that, because this link will be blocking. It's just what side of the link is blocking, because one side will be, and I don't want to throw anybody off with this, but one side will be designated, the other side will be blocking. And that's still as good as blocking. That's still as good as the link, this link being, out of the picture unless something else fails. So to figure out which side is going to be blocking and on which switch we're going to have our designated port, I know this sounds kind of funny because we kind of just went over this with the root ports, but it's pretty much the same thing. Root port is the interface with the lowest or the best path to the root bridge, lowest cost. Same thing with the designated port, lowest cost to the root bridge. So the way I look at it is, okay, so this link right here, let me select a different color. This link right here is between this switch and this switch. So I look at it like this. Which one of these switches has, which end of this link, which would be plugged into each of these switches, would have the best path to the root bridge. So I just look at the switch itself, the switch on each end of the link. And I think, well, from this switch, it would be a cost of 4. From this switch, it would be a cost of 8. So with that being said, this side of the link right here would be the designated port side. And then everything left over is blocking. So the blocked port will be gig 0/0 right here on this switch. So we'll be blocking right here. Okay, so just to recap really quick, root bridge is selected by the lowest bridge ID. On the root bridge, all of its ports are going to be designated ports. On every other switch, there needs to be one root port, and that's found by the interface that is the best path to the root bridge, lowest cost path to the root bridge. Go around, figure out the root port on all of your switches. And then designated ports, same thing. Lowest cost path to the root bridge to figure out what side has the lowest cost. So, like in the example of this one again, cost of 4, cost of 8. Okay, and then of course tiebreaker. So at first, lowest for root and designated ports. Lowest cost, and then the first tiebreaker is bridge ID. So again, we encountered that here with these two links, trying to figure out which one would be the root port, because we had a tie, so we had 8 and 8 to get to the root bridge, and we determined that the lower bridge ID was going to be this one right here, which would make this one the root port. Okay, now last but not least, we have this switch down here at the bottom. And I put this in here to try to throw some people off, but in the end, help them out. So that way, if they ever encounter this, they're not going to be put on the spot and not know what to do. So here we're kind of in the same position as this guy right here. We have two interfaces that would lead to the root bridge, but these two connections are connected to the same switch. So, okay, so let's go through the process. So lowest cost path to the root bridge, well, 4 and 4, so go this way or this way is 4, and then here we're 4 more is 8, and then 12, and then 8 and 12. So we have a tie as far as the cost to the root bridge. Okay, so yeah, right. So that tiebreaker, so we use the tiebreaker, lowest bridge ID. Well, that's where this is a little bit tricky, is because, well, both of these links go to the same switch, and that's where you would it would be most common to have a tie when it comes to the lowest bridge ID. Same switch, same bridge ID. So, okay, now what do we do? Well, the third tiebreaker, well, should I say the second tiebreaker, because the first isn't a tiebreaker. So the second tiebreaker would be lowest interface ID. I should have crisscrossed these to kind of try to throw you off a little bit more. But the reason I say that is because by looking at this, you'll say, oh, okay, easy enough, lowest interface ID, gig 0/1, boom, root port. And you would be correct in saying that. The only reason you would be correct in saying that is because gig 0/1 on this switch connects to gig 0/1 on this switch. It's not the switch you're trying to determine the root port on, it's the switch that it's connected to. So we would be looking at the lowest interface on this switch right here. So if these were crossed, if gig 0/1 went to 0/2 and 0/2 went to 0/1, then this would be the root port, because gig 0/1 over here, it doesn't matter what it's connected to down here. So we look at the switch that it's connected to, lowest interface. The lowest interface is gig 0/1. And that would make gig 0/1 on this switch, the root port. So we've got our root port there, and now we need to determine what port is designated. So we'll look at the lowest cost. We'll start with that. We'll start with the lowest cost to the root bridge, best path. And in this, to figure out the designated port right here, there should be no tiebreaker. Because if we look at this link, just like I showed you up here, if we look at this link, it's between these two switches. So which one has the best way to get to the root? So this switch, which could go up here, so cost of 4, so now we're at 8, cost of 4, well, I guess technically it would be more like this. Cost of 4, since this is blocking, cost of 4, so now we're at 8, and then 12. Or from this side of the link, we would have cost of 4, and then another cost of 4 is 8. So 8's lower than 12. So that would make this port on this switch a designated port. So we would be designated there. And we would be blocking right here. Okay, and that takes care of the loop in the network, because if we were to essentially erase everything that's blocking, so this is kind of what spanning tree does logically, not physically, because spanning tree doesn't actually physically unplug the cable. It logically does this to take away that loop and to give us that ability to have redundant links. So in the event that there's a link failure, it can automatically restore that connectivity. This is what the topology would look like. So if PC1 now wanted to communicate with PC2, since it's framed to this switch right here, say the switch didn't know the MAC address, well, it'll send it here. Send it here, it's going to go nowhere. Send it up here, down here, and to PC2. Boom. So these switches learn the MAC address of PC1 when that frame was sent, because this switch will learn the MAC address of PC1 on gig 3/3. This switch will learn the MAC address of PC1 on gig 0/0. This switch will learn the MAC address of PC1 on gig 0/2. And then when PC2 responds, we're going to learn the MAC address on PC2, or for PC2 on gig 3/3 on this switch, on gig 0/2 on this switch, and on gig 0/1 on this switch. Don't have to worry about flapping MAC address tables, don't have to worry about duplicate frames, and don't have to worry about broadcast storms, because even if a broadcast is sent out, whoops, it's broadcasted as it should. And there's no loop for it to continuously circulate around. All right, I'm going to end this video. I hope that it was helpful. If you do have any questions, feel free to reach out. You can contact me by leaving a comment. You can contact me, send me an email to rob@rmtechcentral.com. If you'd like to see something like this a bit more in depth, like if you're curious about, well, you know, how does so say this link were to go down, how does this switch know to unblock this port? Or if you want to know more about topology change notifications, basically the more intricate workings of spanning tree protocol past the basics, let me know, and I'd have no problem making a video on it. Thanks for watching. I really hope you learned something, and I'll see you in the next video.